Okay, let's have a look then. So we left off last time looking at limits and continuity when we were doing our differentiation chapter stuff. You were there for it last time. I'll, with that in mind, only briefly cover the stuff we already covered. And if you want me to go into any more detail, feel free to let me know regarding it.
Yeah.
But okay, so limits. What's the whole idea of limits? Well, we're basically trying to explore what happens in regards to functions as we get closer and closer to a specific x value. This is specifically different to the actual value at that spot. The way a limit works is you essentially come from the left-hand side of a function until you arrive at the spot that it's asking about, and you do the same thing from the right-hand side. If you get to the exact same spot on the graph, a non-infinity spot, then the limit is said to exist. Otherwise, it does not exist. Specifically, usually in the case of asymptotes, because they'll tend to go towards infinities, even if they are either divergent, going away from each other, or convergent. If they ever approach a certain infinity, we still consider the limit not to exist. From there, we looked at how to actually evaluate some limits. So typically, it's just going to be the case of polynomials divided by themselves. Simply put, if the question is written in the correct way, you shouldn't be able to just shove in x equals whatever directly into your function. You need to do a bit of factorizing and rearranging to get it into a state where you can sub it in without getting any divide by zero errors or any other things that break math, more or less. So in this case here, we're just factorizing the top polynomial and then cancelling out the common factor of x minus 2, thus giving us the limit of 3. Now, worth pointing out, I mentioned it again, the limit being 3 does not mean that y equals 3 exists on this graph. It does not. This graph simplifies down to the linear of 2x minus 1. There will be a discontinuity, an open circle, at specifically x equals 2. So the limit is 3, the value is considered undefined. It's a minor nuance that needs to be internalized when it comes to understanding limits. That's where we left off things last time. I flew through it a bit fast there. Is there anything about any of those concepts that need to be clarified further before we move on? Sweet. That was discrete limits. They are when x is approaching a specific number. What we're going to look at now are what happens if the thing in the limit is tending towards an infinity. There's going to be three main cases, and it's got to do with the degrees of the polynomials involved. So more or less every single time you do this, you're going to have two polynomials, one on the numerator, one on the denominator. And based on how big they are in relation to each other will depend on which of these three outcomes are going to be met. So we've got P for the numerator, we've got Q for, here's a question, degree of polynomials, highest power. Yep, correct. That's exactly right, the highest power. Okay, so P being the numerator, Q being the denominator. If the numerator has a lesser power than that of the denominator, the limit's always going to go to 0. That's just a nice shorthand. All of these are going to be shorthands of the results you'll get. We'll then look at like the more specific as to why that's the case, and also if you forget these shortcuts, you'll still be able to get there anyway. If they have equal degree, then you will get a finite non-zero limit. So it'll be a number, a specific number, but you won't be able to know ahead of time what that is until you actually do some math. This one here, you just always know is going to go to 0. Then, if the degree of the numerator, so the power of the numerator, is greater than that of the denominator, then the limit will always not exist. It'll shoot towards a positive or negative infinity. Those are the three shortcuts. We'll explore in more detail why they are the way they are, and then it'll become easier to understand why they get what they get. In all cases, this is the procedure that you follow for evaluating limits that go to infinity. Let's have a look at what that looks like. So first example, we've got a linear divided by a quadratic. This is going to be a case where the degree of the numerator is less than the degree of the denominator. This is degree 1, this is degree 2. So what we should expect is that it goes to 0 at the end. The problem with limits to infinity is that subbing infinity directly into these spots is somewhat nonsensical, in the sense that you're just going to have infinity divided by infinity, and then you're just going to be like, well, okay, what do I do with that? Instead, what we make use of is doing a bit of rearranging of the fraction that we have, such that pretty much every term involved that has an x in there has its x in a denominator spot rather than a numerator spot. And the way you do that is you just look at the highest power in the entire division, which in this case is x squared, and then either divide top and bottom by x squared, or you can use your negative indexes to keep things a bit neater. I've expressed them as divisions just because it's a bit easier to see what's going on. Negative indexes sometimes get a bit confusing when you're looking at them. Basically put, I'm saying that's the highest power, so multiply top and bottom by x to the power of -2, or in other words, divide everything by x squared. Whatever you do to the top, if you do the same to the bottom, the fraction maintains. In doing so, because, yeah, question?
Why are we multiplying by x to the power of -2 specifically again?
Because it's going to be the highest power in the entire fraction we're dealing with.
Yeah. What's the reason we take it into a negative instead of, because it's x squared there, but
so basically the idea is to divide everything by
oh,
x
okay.
squared. Because what you're trying to do is get every x term in the denominator spot rather than the numerator spot. That's the idea. And whether you do it with negative indexes, a multiplication, or a division, I was kind of just saying you can do whichever makes more sense to you to read.
Okay. Yeah.
So having put them all in the denominator, now we put our infinities in there, it's a bit easier to see what's going to happen to each term, because when you put infinities in those spots, you can basically think of it as just a really massive denominator. And any fraction that has a really massive denominator is approximately just 0. So what you end up with is everything that still has an x involved is just going to effectively be rewritten with 0. And because you've got all zeros on the numerator, well, you end up with a net 0 for the limit. That's the arithmetic approach for solving it. As for just a general sort of remembering as to like why this result is the way it is, you can kind of just think of like infinity being outpaced by infinity squared. It's not at all math sound, but it's just a nice sort of intuitive idea of, well, okay, I got infinity up here, but I got infinity squared down here. That's a bigger infinity in quotation marks on the bottom, and so everything should just condense down to 0 because I've got a massive denominator and a comparatively smaller numerator. That's just a little thing that I personally think of to remember that this is just going to go to 0 anyway, and that'll just save you a bit of arithmetic to get there. That's all really. You can have whatever memorization techniques you want, and the arithmetic isn't that challenging either, so whichever way you want to go about it is fine. We're just going to do that exact same sequence for everything else. So again, looking at the highest power, this one's going to be x cubed, but what we're going to see is they both have x cubes in them. So when we divide everything by x cubed, what we'll see is that the leading terms, the ones that are already x cubed, no longer have their x terms in it. Anything that still has an x, again, goes to 0 because it's a negative index x, it's division. And what you essentially have is whatever the coefficients of your biggest terms are the things that propagate through. All right, so you've got the 4 here and the 1 here. 4 divided by 1 is 4. It's the same thing that happened here. It's just that the leading coefficient of this one was 1, and these were all zeros. So it didn't quite end up mattering for the result there. That's a shortcut for there. If you see that they both have same degree, you just do coefficient of that divided by coefficient of that. And it's just that simple. Lastly, we have an example where we got x cubed divided by the x squared. So what we should expect is that the only thing that's going to contribute anything is going to be this coefficient here of -4. But we're once again going to get a divide by 0 error. And, well, we're kind of back to where we started, which is, okay, once again, dividing by 0. We're kind of just going to tend that towards infinity. I've written specifically negative infinity here because that's what the CAS will give. But as your final answer, you're still just going to say limit does not exist. Yeah, you got a question?
Yeah, what does it mean when we say the limit doesn't exist? Like, what's the significance of that?
Yeah, so the significance was you joined a little bit late. We were talking about it here. The limit exists as long as when you approach from the left, you get to the same spot as approach from the right, essentially. So in this case, you're both converging on the turning point, nice and easy. But in this case, because you're approaching an asymptote, one's shooting up, the other's shooting down, they're not quite heading in the same direction. That's the main idea of whether the limit exists or not. As a further nuance to that, even if these were both shooting in the same direction, because they're shooting towards infinity, not a specific value, we still say limit does not exist because the limit's referring to a specific value rather than infinity, which is mathematically speaking more of a concept than an actual number. So when you get these infinities, that's why I was saying here, you still treat this as limit does not exist because it's shooting off to a different direction. It's shooting off to an undefined end. Fair enough?
Yep.
Sweet. That's the limit side of things. The arithmetic is fairly simple. It's more so the interpretation of the results that's going to be a context switch from what you might already be used to. This idea of approaching a value rather than it actually being that value. We'll do a few practices. I can't imagine anything being too crazy. Actually, here's that example we looked at earlier, right, where you had the discrete limit approaching x equals 2. We did our factorization, cancelling things out. Still undefined there, but the limit is 3. The y value considered undefined, the limit would be considered 3. There's a whole bunch of algebra for it, but I've never seen it need to be done. Let's see. Anything else in here? And I'll throw you some crazier things. Oh, actually, it's going to do discontinuity as well. Let me see. Do we have any specific limit ones before we do that? Yeah, I guess so. And some of them are a bit nonsensical, like this 1a over here, limit of 17 as x approaches 2. I haven't really showed you what's going on with that specifically, but does anyone want to take a guess as to why that's a bit nonsensical? Limit of 17 as x approaches 2.
17 doesn't. It's just a straight line, flat line.
Yeah, precisely. It's got no dependence on x whatsoever. It's just a flat horizontal line. So it's just going to end up being 17 exactly. Some of these are less nonsensical, but still just don't require limits, right? Because if you just shove in 6 here, you're still fine. If you shove in a half here, you're still fine. It's only when they get to, like, the first example would be part F over here, right? Which is there's an x in the bottom. You can't just put a 0 in there directly. You got to do some rearranging first. Same with this one here. If you put a 1 in there, that'll go to 0. Then this one is normal again. 0, 0. This will probably end up going to 0. So just due to the complexity, maybe we'll have a look at k first. And hopefully they've written it in a way where it would actually go to 0. Cool. All right, I'll get some notes here. I'll write down 1k there. And we'll have a look and see if we can evaluate it. X squared minus x minus 10 over x squared plus 5x minus 14. And we're doing the limit as x approaches 2. I'll zoom in on it. Cool. Okay. What might we start doing?
Have a screen grab of the steps.
Yeah, I can get a screen grab of it. Sure. In fact, I might as well just hold it up. It's all on one page, basically. Yeah, actually, I've got a screen grab of it as well. So this is the discrete limits section where we had to go to a specific value. It was less about steps, more about, you pretty much always do this by factorizing, right? So you want to try to cancel out the possibility of a divide by zero error. That already sort of gives it away a bit. Factorizing is going to be involved.
Factorize first part.
Yep, factorizing. It cut off a little bit, but I think you said the numerator specifically. Yeah, how are we going to factorize that? Or perhaps
3x
even...
plus 5, and then multiplied by x minus 2.
So, sorry, you said 3x and what?
3x plus 5 multiplied by x minus 2.
By x minus 2? Yep, sure. Was that like a CAS thing, or do you just do that on your own somewhere?
CAS.
Yeah, sure. If you did have to do it tech-free, do you know what sort of techniques you'd be following?
Yep.
Yeah, sick. Okay, cool. And then, yeah, I mean, the bottom one's almost going to be just as easy, right? It's 7 and 2 there, I think. Positive 7, negative 2. X plus 7, x minus 2. Sweet. We've done our factorizing. What do we need to do from here?
We like to simplify now. I think we take out the denominator.
Well, not the whole denominator, but certainly a part of it can be removed. So we've got the x minus 2 that's a common factor, so those can both disappear, leaving you with just x plus 7 and the 3x plus 5.
And then we, obviously it's a limit equal to 3x plus 5. Do we just make it limit times x plus 7 equals 3x plus 5?
Oh, sorry. So this isn't like limit times. This is just the limit of whatever's in
the limit
brackets
of,
here.
Okay.
Yeah. So basically the notation there is more or less once you got it into a stage where you don't get any weird math shit by dividing by 0 or whatnot, then this just says substitute in x equals 2.
Oh, okay.
So in other words, yeah, 3 by 2 plus 5 over 2 plus 7, which, you know, is just a number. That's the whole idea there, right? So factorizing where applicable, cancelling the like terms out, and finally then, once you don't break math, you can now do your substitution to figure out what the actual limit is. In certain circumstances, maybe in like an exam or SAC situation, you might also want to check and see, hey, did I even have a divide by 0 issue at all? Because if I didn't, there might be a follow-up question involved, like what's the actual value at that spot versus what's the limit at that spot. In this case, is there a value at x equals 2? And if so, or if not, also, what is it? Remember, there's a difference between value and limit. Or I guess more specifically, the y value versus the limit.
Wait, I didn't really clock the question. What was it again?
Yeah, that's fair. So basically, you know, we're going to end up with a result down here. So 6 and 5 is going to be 11, 7, 9. We're going to get a result here at the end of it. A follow-up question to that on your SAC might be, is this equivalent to the value of the function at that spot? We got this result of 11 or 9 by doing our arithmetic. Is that equivalent to the y value of our function?
Not necessarily. I don't think so.
Okay. I mean, not necessarily is a good starting point. Why not necessarily?
Because the limit is when you're approaching a point. It's not necessarily when you're at that point itself.
Yeah, exactly. So if you need to more concretely answer this, how would you know whether or not this is also the value?
You could sub it in. Oh, you could replace a limit with just a value.
Yeah, correct. So you just sub it in directly. And
so
if
would
you
that
sub
just
it
be
in,
like 11 over 9 equals 3x squared minus x minus 7?
So that will be the harder way of doing it, trying to reverse engineer back to x. Basically, the idea would be instead of doing the limit arithmetic stuff, you just sub it in directly and see what you get without doing any cancellation of anything. So a good point to look for first would be testing the denominator, because if the denominator is safe, then the numerator is going to be safe by default. Right, the whole reason we're doing this whole arithmetic here is to make sure we don't get divided by zero errors. And if you do a quick check here, 2 squared gets you to 4, plus 10 will get you to 14, and then minus another 14, well, you're right back to being 0. So the limit here, more or less your answer would be something to the effect of, no, the value would be undefined at this spot due to divide by 0 error, or something to that effect. Just something to interpret the difference between a limit and the actual value, if it exists. In the actual final exam, limit stuff is never touched on. It's more so when you hit your Unit 1 and 2 related stuff that they start maybe asking this in SACs. Maybe even Unit 3, 4 might start asking it in SACs. It is on people's planners, after all. So it might be assessed, but I can say for certain, I'm pretty sure there's only ever been one random multi in the last God knows how many years of exams I looked at that asked anything related to limits or could have been solved with limits. But anyway, cool. Nihal just had somewhere to be, but he'll join back later. We will continue on, unless you want to practice another one of those.
Yeah, sure.
Sure, okay. We can do it together if you want, or maybe even try yourself for L. What do you think?
Maybe we'll do it together, but I'll try the steps and then you'll let me know.
Let's do it. Okay. That'll be, zoom in a little bit more just so I can get more space. Lim of x approaches 1, and that's going to be of x squared minus 3x plus 2 all over x squared minus 6x plus 5. So it's almost like even before starting the question, you want to see, hey, do I even have to do anything to this? The answer may be no. But let's see how we go.
What was the method for discerning that again? Figuring out whether or not you need to, or do you kind of have to go through the process and then?
You don't have to go through the full process. We talked about it at the our last exploration before we moved on to the next question. What was that all about, and what do we do there? Is that all
testing the point at 1?
Yeah, precisely. If you can just shove in x equals 1 here with no issues, then, well, there's, nothing else to be done.
That would be 1 minus 3 plus 2 over 1 minus 6 plus 5. Which is 0. Oh no, but then you get the 0. Okay.
There you go. So a quick little sanity check. Do I even have to do anything? Yes, I got to divide by 0 error. I need to do some fixing.
Okay, so we've got to factorize.
Yep.
1 second. So that gives us x minus 1 times x minus 2. And then I'm doing the bottom one. And then when we factorize the denominator, we get x minus 1 times x minus 5.
Yeah, that's the one. Sick. Cool. Good
and then
so
cancelling out the x minus 1.
Yep.
And then could you go up just to the last question? I think I remember it from there. It was okay, and then we sub in what value the limit's approaching. So we sub in 1, so we get -1 over -4. So 1 over 4.
Yeah, that's it. 1 over 4, and that is the limit. Yes.
I still don't think really properly understood the concept of limit because I get it. Like I understand the process of calculating, but what does the 1/4 like mean? I still didn't really understand that.
Yeah, that's fine.
Like I understand the process, but just not the concept.
Yeah, that's cool. So let's go back to the screen share. They had a picture of it, and that'll hopefully illuminate things a bit better. So we had this example of a quadratic divided by a linear. We go through the procedure, and we're shoving in x equals 2. We get a value of 3, right? What's that all about? Cool. We know it's a limit because it says limit there, but what's the difference, right? Well, this graph is functionally identical to 2x minus 1 when all is said and simplified, because this is just algebra, right? These two are functionally identical, with the caveat that this domain is still applicable here. Because that original function had a discontinuity at x equals 2, after simplification, that domain is going to propagate through. So when you actually look at the graph of 2x minus 1, you're going to get this red line over here, but there's going to be discontinuity there. So basically what you're finding is what would be there if there was a value, right? If it was defined at that spot, what's it converging onto? Because when you come from the right-hand side, when you come from the left-hand side, both of them are converging onto a specific y value, that being y equals 3. That's what the limit's referring to. The actual value of the function is still a white circle, it's still undefined. So
Is there a value for x equals 2 for that equation? Like if you plugged into, or would you get the 0 problem?
you get the 0 problem. Yeah, it's
Okay.
undefined.
Yeah.
And so
Oh, okay. So because we can't sub in x equals 2 to figure out what that point is equal to, we use a limit to kind of estimate what it might be around.
yeah, it's an exploration into discontinuities, basically, which is why it's tied in with the continuity section of the textbook. Because otherwise you don't need limits, you just sub in values and you get what you need. So yeah, it's because what we've done here is a bit of math magic, right? Getting this down to a basic linear. You just got to remember that where it came from, it did still have x minus 2 as a denominator, and therefore the function was undefined at x equals 2. Because if you do all the simplification, it's the same reason why if you've done your log stuff before, it's the same reason why if you condense all the logs down into one log, sometimes the domain doesn't come out to be what you expect it to be. Because you've done some of this math magic in here to be like, oh shit, I've actually lost some information in my log sequence. So one of the things I recommend if you have like an addition or subtraction of several logs and it's domain related, check the domains of each of the individual ones and maybe then combine it all rather than try to simplify it into one log, because you do lose some of that information.
And for the limit, is it better to look at the denominator first? Because, I mean, with this question, you can pretty quickly look at the denominator and instantly see that's going to be 0.
Yeah, super quickly. If the question's written properly, it should always be an issue. It results in a divide by 0, because otherwise there's no reason to put limits in it at all, and your test has just sort of done something to explicitly trick you. But it doesn't even trick you, because you still just do whatever you're doing anyway and gets the result the exact same way. So it's a pretty useless trick because it doesn't actually do anything to you. But it's more so about that follow-up that I mentioned, which is, okay, now they're trying to explore what's the difference between the value and the limit. Are they the same? Are they different? Why? That might be when they'll start doing that sort of stuff. So yeah, a nice little quick check. I'd be like, do I need to do anything special here? Is valid. It takes no time or effort either.
Yep.
Sweet. So it's clearer now, the difference between like well, I guess more or less like what limits you're actually doing.
Yep.
Sweet. Okay, cool. Next up is going to be the continuity section. Well, I guess, did they have any limits to infinity here? I guess that's more so.
With the method for checking whether or not the numerator or denominator has a high degree, that's only for limits approaching infinity.
Yeah, that's right.
Okay.
We use those little shortcuts there because basically those infinities are now going to become zeroed out terms, and we're just sort of seeing what that tends to work towards. Or if you just don't even bother memorizing any of those techniques, you've just got this as well. that works in all cases.
What would happen if you tried solving the limits to infinity, like if you had a discrete variable instead?
So
As in, like,
how
if
do I change it?
instead of x equals is limit approaching infinity was like 2 or something like that. What would happen if you try to solve a limit approaching infinity, kind of normally?
Yeah,
As
like
it
if you
is.
did x equals 2 here, this would no longer have a removable discontinuity, because if you do shove in x equals 2 there, it will go to 0. But there's also no factorizing to be done here. So if we were to plot this graph specifically, let's see what we actually get. Because what you'll find with, yeah, okay, new graph, or new calculator rather. Because what you typically find with the graphs that have removable discontinuity is that they become another polynomial that is just fully sketchable on its own. Whereas if it's unremovable, that is to say you can't factorize it and cancel out a common factor, then what I imagine is, yeah, okay. What I imagine is things get a bit more challenging because you get like asymptotes, more specifically. Okay, where's the graphing thing on this? It's been a while.
Is this the class pad?
Yeah, it's the class pad.
What's different about it from the CAS?
It's worse.
Is this a Casio one?
It's a Casio, yeah.
Okay.
Let's try this. Okay, so we do fraction involved. X plus 3 over x squared minus 4. This might break, so let me do a bracket around this. Save it, graph it, and I think it's one of these buttons. Nice. Why did you draw the green one? I want you to draw the pink one. Oh, it is there, it's just really, really small. Alright, never mind with this. I'm going to bring up the other CAS because it's actually back alive. It's been too long since I've used that one. Okay. X plus 3 over x squared minus 4. My assumption is we're going to have an asymptote at x equals 2. And plus minus 2, actually. So it seems to be the case when you have these asymptotes, you don't actually converge onto a particular value, which makes sense, right? Because the limits are going in, well, the values are pointing in two separate directions entirely. So there's no real arithmetic to do to result in a specific value.
Okay. Yeah, because they're just, yeah, you kind of have the asymptote there. There's no values that correspond.
Yeah. And even if it was more Truncus-like when they're both shooting in the same direction, it's still an infinity. And so you're never going to, by subbing in a specific value in this, get to an infinity. Unless you take the whole, well, I'm dividing by 0, so that should be infinity. Unless you take that approach, but that's a bit flawed. We kind of do it with the limits to infinity thing, but that's only because that's what the CAS will do. The CAS will look at the leading sign there. If you look back at the screen share, with the divide by 0, it'll look at the leading term. If it's negative, it'll make it negative infinity. If it's positive, it'll make it positive infinity. I have a note just to make sure, hey, that still is considered limit doesn't exist. But yeah, fair enough why we have to sort of do things a bit differently for these kinds of things.
Yep.
Cool. Yeah, so the question should be, if it is a discrete limit, should be worded in such a way where it is actually solvable. And if it's not, maybe you just say still limit does not exist. That could be a really nasty trick that might come up. But yeah, it doesn't seem like, at least in this book, Unit 3.4, they don't seem to be going through any limits to infinity specifically. It'll be more so in the differentiation by first principles, which is this whole sequence here, which we'll probably look at more so in like the class 1 stuff when that starts catching up to limits, because the unit 3, 4, you don't do this at all. It's like a unit 1 and 2 exclusive.
Oh wait, so you don't need diff by first principles until 4.
Yeah, you don't execute on it more specifically. Yeah. Anyway, cool. So continuity. I capped off last lesson discussing very briefly that as far as continuity goes, it's something we can clearly observe. We're just looking for any gaps or non-smoothness in the graph that we have, where there's little like jitters and parts that it's not connected. Very easy to spot where you have discontinuities. But as far as methods goes, with proving continuity at a point, it has to meet these three criteria effectively. The first one's the easiest. It's got to actually be defined at that spot. So when your function has a specific domain, it's not defined anywhere outside of that domain. So it's not going to be continuous outside of that domain. Should be fairly obvious. Like in this picture here, right? There's no function to the right or left of this, so it's not going to be continuous there. Next up, the limit has to exist at that spot. We discussed earlier how you would go about that, both in the graphical sense of coming from the right and the left if you have a picture, or in the evaluating sense if you have to literally solve whether or not there's a limit. But in every case, they give you a picture to work off of, so you won't really be doing much solving for this, more so just looking at the picture and analysing the graph. The last one is the weirdest worded one. So basically what they're saying is the limit needs to be the same as the value at that spot. So to give you a basic example of what that would look like, when it's not met, when it's violated, that will be something like this, where if you come from the left and you come from the right, both of those are tending towards this spot here. So the limit is down here, but you do have this floating dark circle up here which says the actual value is up here. Now this is obviously discontinuous, you've got a floating dot for no good reason. It's easy to spot that, but as far as what criteria you'll mention is violated there, you'll mention number 3.
So it would be kind of if you, let's say for example for random equation you have limit of approaching x equals x approaching 2, but then it has to be the same as the use actually subbed in that 2, that it would be the same.
Yeah, it was that whole discussion we literally capped off with last time, which was limit and value are not necessarily always the same. This is saying to be continuous, it has to be the same.
And that graph there, the example, is that a real graph?
Well, I drew that, but there's examples of it all over. They've got a floating dot here, just chilling there. And they've got less egregious examples of it, where they got these little breaks. I drew the dot version just because it's one that is defined at that spot, and the limit does exist, it's down here, but they're just not the same thing. So it's an example where only criteria 3 isn't met. That's probably the only way you could do that. I can't imagine any other way, because for limit to exist you have to basically have a proper curve, but the value has to be elsewhere. But yeah, that's really all it comes to for continuity. It's these 3 criteria that you're looking at. So what I'll do is I'll get a screen grab of specifically that, and we'll look at some graphs and try to analyse things. You'll find it very easy to spot discontinuities. It might be a bit more challenging to refer to what's actually wrong with it as far as the criteria goes. So let's try and explore that a bit. 2A. I'm not going to redraw that because it's going to look significantly worse. So basically going to look for where are the discontinuities and why are they discontinuities in reference to the criteria that's either met or not met. So let's start with like the x equals 3 one, for instance. Clearly discontinuous, has a white circle there. What criteria are not met?
At which point, sir?
Let's start with x equals 3.
Would you say it's not defined because does a white dot mean that it's not actually there?
Correct. Yeah, not defined. There's no other black dot anywhere in that vertical line. So, yeah, that's, I think, the first criteria. Either way, not defined. Just for the sake of... Yeah, go ahead.
Yeah, sorry, I was going to say, what does it mean when we say the limit has to exist at the point?
Yeah, so limit existing, that was the thing we discussed over here, which is they both have to converge onto the same spot.
Okay.
So in the math terms, they write it as the left and right limits. Left being denoted by this negative sign, right being denoted by the positive sign on the value. So in other words, left, right, both go to the same spot. Here it exists, here it does not. One's diverging, one's converging. So as far as those other criteria, this thing does actually have a limit there, because as coming from the right-hand side and the left-hand side of the graph, you're still reaching the same spot. So that criteria 2 is actually met. Criteria 3, by definition, will always not be met if 1 or 2 aren't met, because it's dependent on 1 or 2. You know, the limit and the value are the same. If there's no limit or no value, then, well, they can't be the same. So anytime criteria 1 or 2 aren't met, criteria 3 is also not met. Cool. Let's try the same thing with x equals 4, which, what's wrong with that?
I mean, you could... Does it meet the first criteria?
So first criteria is defined. Why is it not defined?
I'm saying, I think it
does
does.
It meet? Yeah, okay. You said does it meet? Yeah, it does. You're right.
Because there's the graph kind of comes down to x equals 4, the second point at the bottom, but that's not actually defined there. So you have the point kind of at the top.
Yeah.
So I think it meets the first criteria.
Yep.
And then the second one, I think it doesn't meet the second one, because when you look at between x equals 3 and 4, it kind of goes back the opposite way, other way.
Looking between these, it's going... not too sure specifically what you're referring to about between...
Oh no, as in, because I think for the second criteria, it's whether or not the two sides are converging onto the point.
Yes.
Right,
Correct.
so on the right side, it is coming down into that point.
Yep.
But on the left side, the graph's gone out the other way.
That's it. So more or less, basically, left is down here at the white circle, right is up here at the dark circle. Those are not meeting, and therefore the limit does not exist at that spot. They are divergent, they don't converge onto a particular point.
Yep.
And then, yeah, as before again, that also means criteria 3 is not met. Cool. Real quickly, I'll come back anyhow. We're just going to quickly overview the continuity related stuff. So what we were just doing there was exploring, yes, it can be pretty easy to spot when there's a discontinuity. It's literally just white circles and gaps in the function. But we're sort of referring to these 3 criteria to be more specific as to why something is defined or not defined at a particular point. First criteria is about domain. Does it actually exist in the domain? Like, for instance, this graph is only defined from here to here. It's going to be discontinuous out here and out here. Limit needs to exist. That's the whole idea of what we were just discussing there, which is this one's going up to here, this point comes down to here. There is a mismatch on there. They're not level with each other. And lastly was our exploration into the limit not being the same as the value. So limit is down here because left and right go to the white circle when you explore down the line, but up here is the actual value. Very obviously discontinuous, but because those 2 criteria are met, you now have to refer to the 3rd criteria there. I've got them both screenshotted. I got the whole thing screenshotted in the chat if you want to refer to those as we now have a look at another example. There's only one discontinuity here actually, so not not too much to practice on that specifically. Let's give it a shot anyway. So part B, we got one discontinuity. Why? Which of the criteria is met or not met?
the limit doesn't exist at x equals 7?
Yeah, limit does not exist. As coming from the right-hand side, you reach up slightly above 6. As coming from the left-hand side, you're reaching, I don't know, let's call it 3. The y values are they're basically just non-level, more or less. How about the other criterias? So criteria 1, domain. Does x equals 7 exist in the domain?
Yep.
Sweet. Yeah, you got a dark circle in that vertical spot. Cool. And then last criteria, is the limit the same as the value at that spot?
No, because the limit doesn't even exist there.
Correct. Limit doesn't exist, it can't ever be equal to the value. Nice.
So we always check the first criteria, then the second one, because the third one just kind of given.
Yeah, so the third one, as long as the first or second aren't met, the third will also not be met. If the first and second are met, sometimes the third will not be met, with this example here, right? Limit exists because you come from left and right. It's still defined, but it's just defined up here. We also had an example of it actually printed here, not just my shitty MS Paint drawing that was in here. I don't know why this is still here. I could have just as easily done a screen grab of this. But no, you get my MS Paint. Nice. Cool. So question 3 is the same, but they've not given you the picture. They're giving you the piecewise itself. They'll get you to draw out the piecewise as an actual picture, and then do exactly the same thing that we just did here. So yeah, there's realistically not actually anything different to be done there. This will lead us into the final section, which will be differentiability. So differentiability does have a specific definition. A function is differentiable so long as the diff by first principles is met. That's a tall order to actually use in a SAC or exam. So we have much easier ways of going about it, where basically, for a function to be differentiable, all of the criteria of what we looked at for continuity are going to play a role here. Not just for the original function, whatever that is, but also the derivative function as well. So in other words, both derivative and original have to be meeting those 3 criteria. But it's even easier than that, because every time they write these questions, they don't actually really give too much of a shit about the specific criteria. Every single time there's an issue, it's going to be something to the effect of a sharp point in the graph. Whenever you have sharp edges in your graph, you have instantaneously changing gradient. And instantaneously changing gradient means that it goes from being a specific value to another specific value in an instant. And because of that, you're going to have it break. Alright, there's not going to be any smooth joining of... There's no like turning point there. It's not smoothly changing over gradient. You're going to have a break there. And so, rather than you having to worry about doing all of this twice, you can just look at the original functions, know they're continuous because they are naturally continuous, like a quadratic is continuous for all values, doesn't matter what domain you give it, so long as you stay within that domain, of course. So you don't really have to analyze much about f of x, it's more so about analyzing like f dash, what's happening out of that. And so a lot of the time, all you're doing is looking at the joining spots. You're looking at where they join. If it's sharp, you're going to get stuff like this going. Alright, so this is constant gradient that's horizontal and flat. So, oh, these are 2 different graphs. Never mind. Let's try that again. So, the x plus 1, that's a linear. Oh, yeah, Taihan.
Yeah, even if it has an instantaneously changing gradient, but the piecewise functions still like intersect, is like like the one there. Is that still continuous?
So instantaneously changing. It's not. In this case, not instantaneously changing because they have the same value at that spot.
Oh, okay. So, as in because instantaneously changing, as in, on the same x.
Yeah, on the same x you have two different values.
Okay.
Yeah, it is a sharp turn, yes, but it's not a there's no point where it magically jumps from one value to the other.
Yeah. So it's still you would still consider it continuous.
Yeah, so this is fully continuous, and the original is fully continuous. This is therefore fully differentiable for all values of x as per the original domains. Which yeah, we'll see in the notes that I have. Basically, the original graph would look something like this, where it's smoothly joined in. So even though we have a linear that's leading into a quadratic, and the result of that gets us... No, I don't actually have a picture of the derivative graph. The result of that would give us a derivative that had a sharp bend in it. It's more about the sharp bends in the original function, f of x, that cause these issues. Like this one here, constant y equals 1, but at this joining point, x equals 0, you get a gradient of 2, instantaneously changing from 1 to 2. A quick note on how you actually draw that as well. Because it's instantaneously changing, and the original function was purely in terms of f of x, you can't actually give the gradient to any one of those values, oddly enough. Even though this one was nominally inclusive of x equals 0, you'll notice that that doesn't actually propagate over. It's a bit of a weirdness there, so just note that when you do actually draw these derivative graphs, if you have to, when you do have these sharp edges in your graph, the gradient doesn't actually belong to any one particular value, or one particular function, section rather. Cool, okay, so more or less, if it's smoothly joining, it should be fully differentiable for all values of x. If it's non-smooth, like this f of x here, you'll notice there'll be instantaneously changing gradient, and therefore it's non-differentiable at that spot. That is to say, we can't know what the gradient is at that spot. To give you a bit more of a detailed breakdown.
Okay, another question.
Yeah.
Okay, so in calculus, when we take a derivative of something like a quadratic parabola, that without any translations, it's flat at the origin. So when we take the derivative of that, considering like if the parabola was the distance time graph, and if the parabola was the distance time graph, and we took the derivative of it at 0, the derivative will also be 0.
Yeah.
So the velocity will be 0.
Yeah, you'd have velocity 0.
Case. So when does the car actually start? Like, when does the object start moving?
When does the object start moving? Yeah, okay. So we do actually touch on this in a kinematics section. So, yeah, it's kind of like the whole physics thing, which is like your frame of references, because in any given frame of reference, there's no motion, right? So how do we have motion if any given frame of reference has no motion? It's going to be the next infinitesimal time that's possible in your domain where you suddenly have velocity, right? Like if you do your diff at x equals 0.00001 or whatever, whatever your time step resolution is, then that'll be where you finally have your motion. It might also be the case that it has initial acceleration as well. So if that diff, well, that's a quadratic, so it's not going to really have that because it'll go back to just being 0. But if it was like a cubic, for instance, you might have some initial acceleration that'll inform what direction it was headed in before it had velocity 0. But this is more kinematics, but I'm hoping that is explaining things a little bit.
Yeah.
Yeah, okay. This is more so about whether it's differentiable at all. But yeah, you're right, talking about how your distance time graph, when you diff that, you get the velocity, diff that again, you get to your acceleration. Yeah, it would have its velocity immediately after your time t equals 0. Cool, okay, so as far as the differentiability side of things, as I was sort of saying before, you're basically testing that breakpoint, which in this case is going to be x equals 0. It's the handover between the quadratic and the linear. First things first, test if that's continuous. If that's not continuous, then the derivative sure as hell won't be. So test the handover, f of 1 of 0, f2 of 0, they're both the same thing. Nice. When it comes to finding the derivative of this, you'll just find the derivative of each individual part of the piecewise. So that quadratic goes down to this linear goes down to this constant. That's a typo. That should not be inclusive of 0. Should both be non-inclusive there. And then yeah, once again you're testing the value. So the handover is going to be the x equals 0, and what we'll see is that both of them result in 3. Because the handover is good, and these are naturally continuous functions without any like asymptotes or anything weirdness going on, we can be pretty safe to say, cool, both of them are good, therefore the original and derivative are fully continuous, therefore fully differentiable for all values of x in that domain, which in this case is real, all real numbers. And again, the graph was smooth. In another example, again, test for continuity of the original function. Quadratic is naturally continuous, linear is naturally continuous, so we don't have to worry too much about anything except for the handover. So we test the handover, cool, that's done. Get our derivatives, test the handover once again. They are different values, different instantaneously changing gradients, therefore non-differentiable at that spot. Differentiable all everywhere else, just not at x equals 0. That's the gist of it, really. We're about to run out of time on this, so I guess, is there anything conceptually that needs to be clarified there? Because the actual arithmetic of it is just test breakpoint, diff, and shove in values. This is things we've done several times before. Is there anything conceptually that needs to be clarified more? Cool. So as far as, you asking to yourself, when is a function differentiable? Anything with natural curves in it, those are all going to be fully differentiable. No worries at all. A, B, those are all going to be fully differentiable. C, we can see there's a cut there, so it's not going to be differentiable there. This is fine. This is not fine, because you've got this, but you've also got these endpoints as well here, which are non-differentiable for the whole limit reasons. Limit, you can't come from left and right because they have endpoints there. Yeah.
What's the relationship between a graph or an equation being continuous and whether or not you're able to differentiate it? Like, is it necessary for it to be continuous?
Yeah. Yeah, so the original function, if it's non-continuous, like if, for instance, that was your original graph, well, you definitely can't derivative here either. Because if this was your regular f of x, yes, you can do derivative on the left, you can do derivative on the right, but you definitely can't do it here because, well, they're fully separated from each other anyway.
Yep.
Part of that's got to do with we're kind of doing a sort of shorthand to this, because technically speaking you have to validate this, which is the whole diff by first principles thing. It just so happens to be the case that we can massively shortcut that whole process and get there without nearly as much of a headache, at least specifically in methods. I'm sure there might be some weird example in higher level math that makes things a lot harder, but for our purposes this is more than sufficient, just testing those breakpoints. Yeah, so any sharp edges, you just say definitely not differentiable there. For these sorts of things you have to then, sketch the graph and then go off of that. And that'll about do it for chapter 9 diff. As of next week we'll start looking at like the applications of diff, doing the tangents and normals, rates of change related stuff. Yeah, actually applying our diff to things. So if there's no further questions, feel free to enjoy the rest of your day. Otherwise I'll stick around for a little bit.
Thanks, Chris.
Thank you.
Thanks. Have a good day.
You too, mate. Take care.